Every day, millions of Americans open a bag of jackfruit chips and see it as a healthy, convenient snack. But very few ever stop to ask a simple question. Where do these crispy slices actually come from? And what do they go through before reaching a supermarket shelf? That journey doesn't begin in a factory. It begins in tropical jackfruit orchards in Thailand, where each fruit is harvested, transported, and handled not as fresh produce, but as an industrial raw material. And from this starting point, a tightly controlled chain of decisions and processes comes together, forming what has become a global standard for jackfruit chips. In the production of jackfruit chips, the goal at harvest is fundamentally different from harvesting fruit for fresh consumption. Farmers are not picking jackfruit to be eaten immediately. They are harvesting a raw material optimized for industrial processing. Timing is the most critical factor. Jackfruit intended for chips is not harvested fully ripe on the tree. Instead, farmers select a stage known as physiological maturity, when the fruit has reached full size and internal development, but the flesh remains firm enough to withstand transportation and downstream processing. Growers rely on external indicators to determine this stage: evenly expanded spines, a shift in peel color from deep green to a lighter shade, and a dull, hollow sound when the fruit is gently tapped. Harvesting is done entirely by hand. A single jackfruit can weigh anywhere from 10 to over 20 kilograms, making experience and coordination essential. The stem is cut cleanly, leaving a short section intact to minimize damage to the fruit's internal structure. At no point is the fruit allowed to drop freely. Even a hard impact can compromise the flesh inside, while leaving the exterior seemingly intact. Immediately after cutting, latex sap begins to flow from the stem. This is a natural process, but one that must be carefully managed. The fruit is typically placed stem side down for a short period to allow the sap to drain, then wiped clean before moving on. If this step is mishandled, sap residue can stain the peel and interfere with later grading and acceptance at the factory. One notable aspect of Thailand's jackfruit system is that initial sorting begins directly in the orchard. Fruits that are misshapen, pest-damaged, or unevenly developed are removed early. This reduces pressure on processing facilities and ensures that only fruit meeting industrial standards enters the supply chain. At this stage, jackfruit is no longer treated as a simple piece of fruit. It becomes a unit of raw material, evaluated for uniformity, processability, and compatibility with the production line ahead. This mindset, treating agricultural products as industrial inputs from the very beginning, is a key reason Thai jackfruit chips achieve consistent quality on the global market. Once jackfruit is cut from the tree, it enters a stage just as critical as cultivation itself: transportation. In the jackfruit chip supply chain, this is not simply about moving produce from point A to point B. It is a race against time and environmental conditions. Jackfruit intended for processing is typically delivered to the factory very quickly, often within 24 hours of harvest. The reason lies in the fruit's biological structure. Even when harvested at physiological maturity, enzymatic activity inside the fruit continues. If transport is delayed or conditions are poorly controlled, the internal tissue can begin to change, reducing heat tolerance and directly affecting the quality of the final product. During transport, fruits are handled with care. They are placed individually or cushioned with straw to minimize pressure and prevent compression damage. Transportation is usually carried out using small trucks or specialized transfer vehicles covered to protect the fruit from direct sunlight. In major growing regions, farm roads and collection hubs are intentionally designed to shorten the distance between orchards and factories, reducing the risk of deterioration during transit. An additional layer of control takes place at intermediate collection points. Here, jackfruit is weighed, harvest time is recorded, and a preliminary inspection is performed. Fruits showing signs of bruising, cracked skin, or abnormal sap leakage may be removed before reaching the factory. This early screening helps maintain a consistent flow of raw material and prevents disruptions further down the production line. The first step inside the factory is raw material intake and inspection. Each batch of jackfruit is logged with information on harvest time, origin, and external condition. Traceability at this stage is not only essential for internal management, it is a mandatory requirement for products destined for international markets. The factory also performs a rapid assessment to determine whether incoming fruit aligns with the day's production capacity and quality targets. Once accepted, the fruit enters the washing stage. The purpose here is not to clean the edible portion, but to remove soil, debris, and microorganisms accumulated on the peel during farming and transport. Washing is performed using clean water and, in some cases, food-safe treatments that comply with international safety standards. This step plays a crucial role in reducing the risk of cross-contamination during subsequent cutting and handling. Next comes detailed sorting. Not every jackfruit that enters the factory is destined for processing. Based on size, shape, uniformity, and peel condition, fruit is divided into specific categories. Jackfruit that is too small, too large, or shows signs of mechanical damage is removed from the main processing line. Making these decisions early helps the factory avoid costly quality issues later in the process. What stands out is that sorting is not based solely on appearance. The criteria are technical and product-driven. Jackfruit chips require flesh with consistent structure, shape retention, and predictable behavior under low-temperature vacuum frying. As a result, material selection at this stage is about functional compatibility, not just visual inspection. In Thai processing facilities, washing and sorting act as a critical filtration system. They determine not only material yield, but also the efficiency, energy use, and stability of the entire production line. Inconsistent raw material leads to uneven processing times, higher energy consumption, and greater difficulty in maintaining product quality. After washing and sorting, jackfruit enters the most labor-intensive stage of the entire production line: peeling, segment separation, and the removal of fiber and seeds. Even in modern, well-equipped factories, this step still relies heavily on human hands. The reason is simple. Jackfruit's internal structure is complex, and the final product demands a high level of precision in shape and consistency. The process begins by cutting the fruit lengthwise. Jackfruit peel is thick and tough, and it must be separated carefully from the flesh to avoid damaging the segments inside. Unlike many fruits, jackfruit flesh is not evenly distributed. Edible bulbs are embedded between dense layers of fibrous material. Because of this, peeling cannot be rushed or done mechanically without risk. A single careless cut can deform the segments from the very start. Once the peel is removed, workers separate the jackfruit bulbs from the central fibrous core. This step directly determines the future shape of the jackfruit chips. The more intact the segments remain, the more uniform the chips will be after processing, with less breakage and higher commercial value. Damaged or misshapen bulbs are typically diverted to secondary product lines or removed from the main process entirely. Fibrous material and seeds are removed completely. For snack production, these components have no functional value and can negatively affect texture if left behind. Clean separation ensures that each jackfruit segment will later interact evenly with heat, a critical requirement, especially during vacuum frying. What stands out is that this stage is guided not only by individual skill, but by strict technical standards. Segment thickness, length, and overall shape are all controlled within defined ranges. These parameters are not arbitrary. They are based on production experience and on how the fruit behaves under vacuum frying conditions. Segments that are too thick struggle to release moisture evenly, while those that are too thin may darken or fracture during processing. In Thai factories, peeling and segmenting are typically arranged in open production lines, allowing continuous supervision. This setup makes it possible to detect inconsistencies early and correct them immediately, rather than allowing small errors to carry forward into later stages. From a production perspective, this step represents the intersection of agriculture and industry, where a natural, irregular fruit is carefully standardized to meet the demands of a modern, high-precision food process. After peeling and segmenting, the jackfruit is still not ready to move directly into drying or vacuum frying. Before entering high-temperature processing, the fruit must go through a series of pre-treatment steps designed to stabilize structure, color, and thermal behavior. This stage often receives little attention, but it plays a critical role in determining the final quality of jackfruit chips. The first step is washing the jackfruit segments again. Unlike the earlier washing of whole fruit, this stage focuses entirely on the edible portion. The goal is to remove any remaining latex, fine fibers, and debris generated during cutting and separation. If left untreated, these residues can lead to discoloration, off odors, or inconsistent crispness after processing. Next comes antioxidation treatment. When jackfruit flesh is exposed to air, natural enzymatic reactions can cause the surface to darken. For international markets, color consistency is nearly as important as flavor. To address this, factories apply food-safe treatments that slow oxidation, helping the fruit retain its natural golden yellow color throughout the processing cycle. After treatment, the segments are allowed to drain and dry at the surface. Surface moisture is a key variable in vacuum frying performance. If the fruit is too wet, heating becomes less efficient, and moisture removal is harder to control. If it is too dry, the cellular structure may be compromised before the main processing step even begins. For this reason, drainage time and environmental conditions are tightly controlled. A final size grading is also performed at this stage. Segments are grouped based on thickness and relative size to ensure uniform behavior during thermal processing. In large-scale production, this level of consistency is essential. It allows each batch to respond to heat in a predictable way, improving line efficiency and ensuring stable product quality. Once this stage is complete, the jackfruit segments are fully prepared to enter the core technology of the jackfruit chips industry. A final size grading is also performed at this stage. Segments are grouped based on thickness and relative size to ensure uniform behavior during thermal processing. In large-scale production, this level of consistency is essential. It allows each batch to respond to heat in a predictable way, improving line efficiency and ensuring stable product quality. Once this stage is complete, the jackfruit segments are fully prepared to enter the core technology of the jackfruit chips industry. Inside the vacuum frying chamber, the jackfruit segments are heated under tightly controlled conditions. Moisture within the fruit slowly evaporates, creating the porous internal structure that consumers recognize when they bite into a crisp jackfruit chip. The process is gradual and stable, allowing the segments to retain their original shape rather than shrinking or deforming, which often happens under high heat processing. Another key advantage is the preservation of color and aroma. At lower temperatures and in a low oxygen environment, the chemical reactions responsible for browning and flavor degradation occur much more slowly. As a result, the finished product retains its natural golden color and the characteristic aroma of ripe jackfruit, rather than the oily smell or bitter notes often associated with conventional frying. After frying, the jackfruit chips move into an oil removal stage using centrifugal separation. Although oil is used during frying, this step removes most of the surface oil from the product. The result is a cleaner mouthfeel and a nutritional profile that aligns more closely with health-conscious consumer expectations in markets such as the United States and Europe. When compared side by side, the differences are clear. Traditional hot air drying often produces a hard texture, darker color, and muted flavor. Atmospheric pressure frying can achieve crispness, but at the cost of higher temperatures, more oil absorption, and a greater risk of scorching. Vacuum frying occupies the middle ground, combining crisp structure with precise control over quality. Importantly, this technology cannot perform effectively on its own. Slice thickness, surface moisture, and raw material uniformity all directly influence the outcome inside the frying chamber. Vacuum frying is not a standalone solution, but the core component of a fully integrated system designed from start to finish. By the time the jackfruit segments leave the vacuum fryer, they have fundamentally changed. What began as raw agricultural material has become a finished product, defined by structure, flavor, and consistency. Before leaving the factory, jackfruit chips must pass through a strict quality control stage designed to ensure consistency and safety for international consumers. At this point, the product is evaluated across multiple criteria. Crispness is assessed first, as it reflects whether moisture removal and internal structure have reached the required standard. Color is monitored closely as well, since unusual darkening may indicate overheating or uneven raw material quality. Residual moisture content is also measured to ensure the chips remain stable during long-term storage without becoming soft or deteriorating over time. Once the product passes quality inspection, it moves into the packaging stage. Packaging is not simply about protection. It is an extension of the quality control system. Vacuum sealing, or the use of inert gases, helps slow oxidation, extend shelf life, and preserve the product's texture and flavor. Each package carries traceability information, documenting the full journey from raw material to finished product. For international markets, especially the United States and Europe, standards related to food safety, hygiene, and process control are non-negotiable. Factories in Thailand have built production systems that meet these requirements not just to comply with regulations, but to establish long-term trust with distributors and consumers. As a result, jackfruit chips are no longer a regional specialty. They have become a global product with predictable, repeatable quality. When the products leave the factory, a new journey begins. Cases of jackfruit chips move through distribution centers and warehouses before reaching supermarket shelves around the world. At that point, consumers see a lightweight, convenient snack, ready to eat, rarely aware of the complex chain of decisions, controls, and technologies behind it. If you'd like to continue exploring how different countries contribute to this global supply chain, follow the next videos on this channel. Subscribe to uncover the stories behind everyday agricultural products, where technology, people, and systems come together to create global value. When harvest season arrives, an onion field can look almost completely transformed. Instead of neat rows of green tops, the surface becomes flatter and more open. This is when machines take center stage in the entire harvest process. On large farms, onions are rarely pulled by hand. The work is handled by specialized harvesters designed specifically for crops, whose bulbs sit entirely below the soil surface. These machines move slowly but continuously, traveling down each bed with high precision. Each row is processed only once, but the goal is to lift every single bulb cleanly onto the surface. The first step is managing the tops. The machine knocks down or cuts the leafy tops above ground. This doesn't just make digging easier, it also signals that the onion has officially reached the end of its growth cycle. From that point forward, the bulb will not grow any larger, and everything that happens next is focused on protecting its quality. Immediately after, the harvester's digging blade runs beneath the soil. That depth isn't chosen at random. It's calculated based on the onion variety, soil conditions, and field moisture. Dig too deep, and the bulbs can get scuffed from heavy contact. Too shallow, and part of the bulb may be left behind. That's why modern harvesters allow operators to fine-tune the settings precisely, keeping losses as low as possible. As the blade lifts the bulbs, the soil is shaken off almost instantly. Most of the dirt falls back into the field, while intact onions are gently laid onto the surface. This happens continuously, forming long, straight windrows across the field. It's the signature image of mechanized onion harvesting: fast, uniform, and controlled. One of the biggest advantages of this method is speed. Under good conditions, a single machine can cover the same area that would require dozens of manual workers in the same amount of time. But speed isn't the only goal. Even more important is the consistency of the onions after harvest, because that uniformity directly affects how well the next steps will run. For growers, this moment carries real weight. The value of the entire season becomes visible right there in the field: how many bulbs remain intact, how much scuffing occurred, and what the overall loss rate looks like at a glance. A precise harvest can determine the profit margin for the entire crop. After onions are lifted out of the ground, they aren't shipped out immediately. Instead, they're arranged in long rows and left right there in the field. This is a critical step that prepares them for storage and for what comes next in processing. This stage is often referred to as field curing. Over the following days, onions are exposed directly to airflow, sunlight, and wind. The outer skin gradually dries, while the neck tightens and seals. Once the neck is fully dry, the risk of microbes getting inside the bulb drops significantly. Curing time isn't fixed. It depends on the weather and the variety. If onions are collected too early, leftover moisture can cause rot during storage. But if they're left too long under intense heat, the onions can lose too much moisture and drop in market quality. That's why growers closely monitor the skin and the neck condition to decide the ideal time to move forward. Once the onions reach the desired state, a collecting machine begins picking them up and feeding them onto a conveyor. Any remaining soil continues to be shaken away as the onions prepare to leave the field and enter the factory environment, where control standards are far stricter. After collection, onions are typically loaded into large bins or transferred directly onto specialized trucks. These vehicles are designed to reduce impacts during transport. Onions do have a protective outer layer compared to more delicate produce, but even small abrasions created during transport can become entry points for microbes if they aren't managed properly. The distance from field to plant might be just a few miles, or it could be several dozen, depending on the production system. Either way, the goal is the same. Get the onions to the plant as quickly as possible, especially in hot weather or high humidity. Unnecessary delays can increase spoilage risk and reduce storage potential later. Once the truck leaves the field, onions enter a completely different environment. No more sun, wind, or soil. Now it's metal, conveyors, and an enclosed, controlled space. That shift requires a much higher level of sanitation and handling discipline. Mistakes during transport can ripple through the entire processing line. At the receiving area, onions are unloaded in a controlled way. Bins may be tipped or opened from the bottom, so onions drop gently onto the intake conveyor. At this stage, the plant usually performs a quick initial inspection, checking the overall condition of the load, how dry the skins are, the level of scuffing, and size uniformity. For the processing plant, this isn't just intake, it's the first step in standardizing raw material. From this point forward, onions are no longer treated as a field-harvested crop, but as an industrial input moving through a defined closed-loop system. Once onions enter the plant's processing line, the first major step is cleaning and sorting. It's a crucial filtering stage because not every bulb harvested in the field is suitable for further processing. Cleaning begins as soon as onions move onto the conveyor. Dirt and debris left from transport are removed using vibration systems and strong airflow. Some plants add a water rinse, while others prefer dry cleaning to avoid introducing moisture. The method depends on the final product and the sanitation standards the facility follows. After debris is removed, onions move into sorting. Here, each bulb is assessed for size, shape, and exterior condition. Onions that are too small, too large, cracked, or showing signs of damage are removed from the main line. This isn't just about quality. It also helps downstream steps run more smoothly and efficiently. In modern facilities, sorting may be supported by sensors and camera systems. These can catch issues that are difficult to spot with the naked eye, like small bruises under the skin or subtle color differences. As a result, the number of substandard onions entering deeper processing is reduced significantly. From a production standpoint, this step is decisive. A single defective onion that slips past sorting can affect an entire batch, especially for ready-cut or fresh-packed products. That's why many plants accept a certain rejection rate early on in exchange for long-term quality consistency. For onions that remain on the line, cleaning and sorting also standardize the input. Bulbs that are similar in size and condition can be processed using the same machine settings later, improving precision and reducing losses during peeling or cutting. By the end of this stage, most contaminants and non-conforming bulbs have been removed. The onions are ready for more aggressive handling, where the protective outer layers are stripped away and the natural shape of the onion begins to change. Peeling is typically done using specialized equipment. Instead of peeling each onion by hand, the plant combines strong air jets and abrasive surfaces to remove the dry outer skin. Because that skin was already dried during field curing, it can be separated relatively easily without damaging the flesh underneath. Control is critical here. Too much force can scuff the fresh layer, while too little leaves peel behind and hurts product quality. After peeling, onions move through top and tail removal. The root end and neck are trimmed to create a uniform size and shape. This makes the onions better suited for the cutting machines that follow, and removes areas where microbes can more easily accumulate during storage. From here, onions can be cut into multiple formats depending on the final product. Industrial cutters are designed to produce consistent thickness, whether the output is rings, strips, or diced pieces. Blade speed and spacing are precisely controlled, so each cut meets the same dimensional standard. At this stage, uniformity becomes the key factor. Uneven pieces can disrupt downstream processing, especially drying, freezing, or frying. That's why plants routinely inspect and recalibrate equipment to maintain accuracy across an entire shift. Technically, peeling and cutting mark a major transition. The onion is no longer treated as a whole bulb. It becomes a semi-processed ingredient. Its properties change immediately. Surface area increases, exposure to air rises, and sanitation requirements become much stricter. And this is the point where onions start branching into very different outcomes, depending on how they're cut and what processing step comes next. Once onions are peeled and cut into specific formats, they no longer follow a single path. From here, they're split into multiple processing streams, each designed for a different use case and a different market. This is where the value of the onion can change dramatically. Some onions remain in a ready-cut form for the fresh market. Rings, strips, or diced onions are packaged under strict sanitation and temperature control. These products typically have a shorter shelf life and are distributed quickly to supermarkets, restaurants, or institutional kitchens. The main advantage is convenience, but that convenience depends on a stable cold chain to maintain quality. Another stream goes into freezing. After cutting, onions are rapidly frozen at very low temperatures to preserve texture and flavor. Frozen onions can be stored much longer and are commonly used in processed foods, especially in ready-to-cook items or for export. A large volume is also sent to drying. Drying removes a significant portion of the onion's water, extending shelf life and lowering transportation costs. Dried onions may be produced as flakes, pieces, or granules, and they're widely used as intermediate ingredients across the food industry. From dried onion, the plant can go one step further and mill it into onion powder. This is a high-value product in seasonings and processed foods. Onion powder stores well, blends easily, and delivers strong flavor in small amounts, while still retaining the characteristic onion profile. Another processing route is producing fried onions. Thinly sliced onions are fried in oil at controlled temperatures, then de-oiled. Fried onion products are used extensively in ready-to-eat foods and packaged meals, where flavor and crisp texture are essential. Each processing stream requires different technical standards for cut size, moisture level, and sanitation. That's why early product routing is so important. It helps plants maximize efficiency and reduce waste. From a single onion bulb, multiple products can be created, each serving a specific role in the food supply chain. And once deeper processing is complete, onions move into the final stage. After all processing and conversion steps, onions enter the final stage inside the plant, packaging. This is where the product becomes most clearly defined, not only in appearance, but also in quality standards and how well it can move through the market. Packaging is designed differently depending on the product. Ready-cut fresh onions and frozen onions are typically sealed in packaging that blocks moisture and helps maintain stable temperatures. Each package is filled to an exact weight, ensuring consistency from unit to unit. For dried onions, onion powder, or fried onions, packaging must also protect against oxidation and extend shelf life. Throughout packaging, sanitation is the top priority. Packaging areas are usually enclosed spaces where temperature, humidity, and human contact are tightly controlled. Machines handle most of the work, from filling and sealing to labeling and applying traceability codes. Every package leaving the line carries batch-level identifiers tied to production time and standards used. For the plant, packaging isn't just the final touch, it's what determines distribution success. A product packaged correctly will hold its quality through shipping, storage, and retail display. A small packaging mistake, on the other hand, can reduce the value of everything that came before it. When the last cartons are stacked onto pallets and prepared to leave the facility, the onions have completed their industrial journey. What began as a bulb under the soil has become a product ready to show up in everyday meals for millions of people. If you found this behind-the-scenes journey interesting, take a moment to follow the channel and share the video. And in future episodes, we'll explore the stories behind other familiar crops, things you see every day, but rarely get to witness from start to finish. What you're watching isn't hand harvesting. This is industrial sugarcane harvesting, where every motion is measured in seconds. The machine in front of you is a fully mechanized sugarcane harvester. One pass, and it can replace dozens of laborers, processing tens of tons of cane per hour. And the process starts instantly. The first part to go is the top of the cane. Rotating blades slice off all the leaves and tender tips. This part doesn't go into sugar production. It falls back to the ground as a natural mulch, retaining moisture and protecting the soil for the next crop. It all happens in the blink of an eye. No stops, no slowing down. Next, another set of blades works close to the ground. They cut the cane just a few inches above the soil. This is the most important part of the plant, the section with the highest sugar content. Cutting so close not only maximizes sugar yield, but also leaves roots in place so the cane can regrow for the next harvest. Once the stalks are cut, massive rotating rollers swing into action. They lift, gather, and pull the entire stalks into the harvester. In just seconds, a row of cane taller than a person disappears as if it never existed. It's a moment that leaves many in awe. The cane doesn't topple into a mess, it vanishes. Inside the machine, the stalks are no longer whole. High-speed blades cut the cane into uniform, short pieces called billets. Each piece is nearly identical in length. This size makes the cane easier to transport, easier to press, less likely to get damaged. Everything happens continuously, without pause. Just before leaving the machine, a powerful fan system kicks in. Dry leaves, dirt, and light debris are blown away. What remains are the cleanest billets possible, ready for the next stage. From above, the scene looks like a giant machine is eating the field. Every minute, hundreds of cane stalks vanish, tons of raw material are processed, and the operation keeps moving forward. No chaos, no waste, only technology, rhythm, and efficiency. And this is just the first step of the journey. The moment the cane leaves the harvester, it never touches the ground. Next to the machine, a truck or trailer waits, moving in perfect sync, matching speed, maintaining precise distance. From the top chute, the billets are shot directly into the vehicle's bed. No stopping, no waiting, no middle steps. Everything happens simultaneously. Each truck is quickly filled with tens of tons of fresh cane, and the moment it's full, it pulls away, immediately replaced by the next one. The field never pauses. This isn't just transportation, it's high-speed agricultural logistics. From the instant a stalk is cut, the clock is already ticking against it. Sugar in the cane begins to break down. Bacteria and fermentation quietly start their work. Time is the enemy. At an industrial scale, even an hour of delay can mean lost sugar content. The mill gates swing open. From this point on, everything moves to an industrial rhythm. Trucks carrying cane enter the reception area one by one. Each load is weighed with precision, logged, and randomly sampled. Not for show, it's about quality control. Sugar content, moisture levels, impurities, all checked in seconds. Here, every percentage of efficiency counts. Next, the cane is dumped directly onto conveyor belts. No storage, no waiting. From above, the moving cane looks like a pale green river flowing straight into the heart of the mill. Before it can be pressed, the cane must be cleaned. Large rotating drums start to tumble and agitate the stalks continuously. High-pressure water jets wash away remaining dirt and sand. Powerful fans blow away dry leaves, straw-like debris. Anything that doesn't belong in sugar is removed at this stage. It's a step often overlooked, but absolutely critical. Even small traces of soil or sand can wear down the rollers. Dirty, the juice reduces the final product quality. So, before the cane goes further down the production line, it must be as clean as possible. In just a few minutes, the rough stalks harvested from the field have been transformed into standardized industrial raw material, ready for processing. If the sugar mill were a living organism, this area would be its heart. All the value in the cane, the work of farmers and the entire harvesting chain, comes down to this moment. Before the stalks meet the massive rollers, they don't go straight in. The clean cane passes through high-speed choppers, shredded into long fibers. The goal is simple: increase surface area. The more exposed fibers, the easier it is to release the sugar inside. This is the opening act before the real pressing begins. Once chopped, the cane enters the roller mill. where physical force reaches its peak. Each roller is a steel giant weighing tens of tons. They spin slowly and evenly, but generate enormous pressure. The cane isn't crushed all at once. Instead, it passes through multiple rollers in sequence. Each roller presses harder, extracts more cane juice, pulls every last bit of sugar left inside. With each pressing, a cloudy brown liquid starts to flow. Raw cane juice. This is the defining moment. Sugar is finally released from the stalks. The juice is collected continuously, funneled through large pipes deeper into the mill. The flow never stops. There's no pause because the rollers behind keep pressing. Between rollers, hot water is sprayed counterflow. The goal isn't cleaning the cane, it's washing out the remaining sugar. At an industrial scale, leaving just a few percent behind can mean massive losses. So the pressing process is optimized to the max. Multiple presses, multiple washes, capturing nearly every drop of sugar from the stalks. After the final roller, what remains isn't whole cane anymore. It's bagasse, dry, fibrous, almost sugar-free. But it's far from trash. Conveyed directly to the boiler, bagasse is burned as fuel. It creates steam electricity energy to run the entire mill. In other words, the mill powers itself with the cane. During harvest season, the roller mills operate nearly 24/7. Stopping isn't just a delay, it can cause damage and huge losses. So the rhythm is relentless. Cane continuously fed in juice, continuously extracted bagasse continuously removed. It's a steady, powerful, unforgiving cadence. By the end of this stage, the cane has completed its role. What's left is raw cane juice, cloudy, hot, full of impurities. It's not sugar yet, not even close. But the journey has now taken a new turn. The liquid leaving the roller mills doesn't look anything like sugar. It's dark, cloudy, hot, and packed with all kinds of impurities. Fine soil fibers, proteins, plant waxes. If you tried to crystallize it now, you'd end up with dark, off-flavored sugar of poor quality. That's why the next step is cleaning, clarifying the juice. Raw cane juice is sent through a heating system. The temperature rises quickly, near boiling. The goal isn't to cook the sugar, it's to prepare for the chemical reactions that follow. When hot, impurities clump together and become easier to remove. A precise amount of lime, calcium hydroxide, is added to the juice. Not too much, not too little. Lime changes the pH, causing impurities to clump together, become heavier, separate from the sugar solution. This step requires tight control. Even a small deviation can affect the entire downstream process. After the reaction, the juice flows into large settling tanks. Here, everything slows down. Heavier impurities sink to the bottom, forming filter mud. The liquid above gradually clears, becoming brighter and more transparent. The difference is striking. From a murky stream, the juice transforms into a pale golden, clear, and stable liquid. For viewers, this is one of the most visually rewarding moments. No noisy machines, no enormous pressure, just heat, chemical reaction, patience, and the results are undeniable. After filtering, the result is called clarified juice. It is low in impurities, stable, ready for the next step. But remember, it's still a liquid. Sugar is dissolved, not crystallized. There's nothing you could hold in your hand yet. The journey is entering a new phase. By this stage, the cane juice is clean, but it's still just water with sugar dissolved in it. To turn it into real sugar, the mill must do something that seems simple. Remove the water. And that's where the evaporation process begins. The clarified juice flows into a multi-stage evaporation system. These massive machines run continuously, non-stop. Rather than boiling the juice directly, the mill uses a vacuum to evaporate water at lower temperatures. This method saves energy, prevents burning. The sugar maintains product quality. Little by little, water disappears. The solution thickens, becoming syrupy and darker. After multiple evaporation stages, it's no longer just cane juice. It has become a sugar syrup, thick, slow-flowing, glossy. Sugar now makes up most of the volume, but it's still invisible to the eye. Everything remains dissolved. The syrup is transferred to vacuum pans for crystallization. This is the most critical stage in the entire mill. Pressure is lowered further. Temperature is controlled with extreme precision. When conditions reach the perfect point, the syrup can no longer hold the sugar in solution. And then, the first crystals begin to form. At first, they are almost invisible, tiny specks suspended in thick syrup. But over time, crystals grow larger. Edges sharpen shapes, become distinct workers constantly monitor. Temperature timing crystal size. Because, too fast, crystals remain small, uneven, too slow, clumping, hard to separate. Everything must happen at exactly the right moment. This is the moment the whole journey has been heading toward. After hours of processing, through countless mechanical and chemical steps, sugar finally appears in solid form. No longer liquid, no longer a solution. Real sugar crystals. Even now, the crystals are still bathed in thick syrup. They must be separated, and that requires even more force. After crystallization, the sugar exists in solid form, but it's not ready to use yet. The crystals are still soaked in thick syrup, sticking together, wet and heavy. To get loose, dry, sparkling sugar grains, the mill must separate them. The mixture of crystals and syrup is fed into high-speed centrifuges. Metal drums spin at thousands of revolutions per minute. Centrifugal force pushes heavier sugar crystals to cling to the drum walls, liquid syrup to be flung outward. In just seconds, two components that were tightly bound are completely separated. What's expelled isn't waste, it's molasses, a high-value byproduct. Molasses is used for ethanol production, animal feed raw material for other industries. In a sugar mill, almost nothing is discarded. The sugar remaining in the centrifuge is wet. Crystals are separated but still high in moisture. If packaged now, it would clump, spoil easily, and be unstable in storage, so the journey isn't over. The wet sugar moves into a drying system. Hot air blows continuously, gently but strongly enough to remove the remaining moisture. The crystals begin to dry out, become lighter, fully separate. Then, the sugar is quickly cooled, stabilizing the structure before moving on. At the end of this stage, the sugar takes its familiar shape. Loose, dry, bright white crystals flow evenly along the conveyor belts. After drying and cooling, the sugar doesn't stop on the conveyor belt. Before leaving the mill, these crystals must pass the final quality checks. The sugar moves through vibrating screens and sensors. Crystals are sorted by size, uniformity, moisture content. Any grains that don't meet standards are sent back for reprocessing. Only crystals that pass all checks are allowed to move forward. From this point, sugar takes on the familiar form seen in stores. In the packaging area, the process is nearly fully automated. Machines weigh each batch, precisely fill. Bags seal the tops, print traceability information. Depending on the intended use, sugar is packaged as 25 or 50 kilos industrial bags for food manufacturers, smaller bags for retail. Everything happens continuously, with minimal human intervention. Finished bags are neatly stacked onto pallets by robots. They are then wrapped for protection and moved into storage. The sugar warehouse is always dry and cool, strictly controlled. Even a small change in humidity can affect quality. From the mill, the sugar begins a new journey. These pallets will be delivered to food factories, distributed to retail chains, or transported thousands of miles for export. All of this happens within a precisely calculated supply chain. At this stage, sugar is no longer just a product on a production line. It has become a commercial commodity, an essential ingredient, a familiar part of everyday life. From a distant sugarcane field to the warehouse, and finally to the supermarket shelf near you. Just a few hours ago, these were still stalks of cane standing quietly in the field. They have now been harvested, transported, pressed, clarified, concentrated, and crystallized through a chain of processes, precise down to the smallest detail. No step is wasted, no room for error. And in the end, it all comes together in the tiny, white, familiar sugar crystals. We use it every day. What's remarkable isn't the sugar itself, it's the journey behind it. a journey most of us rarely see. If you're curious about how large-scale agriculture and industry truly operate, from the fields to the mill, and finally to the market, keep following the channel. Countless silent processes are happening every day, and they're worth seeing.